Welcome to section 4, about binary trees. In this section, we will look at the workings of both unbalanced and self-balancing binary search trees, and how to implement them in a functional manner. In this first video, we will learn how binary search trees work. First, we will introduce the idea behind binary trees, and the types of problems they are used for. We will then have a look at how searching and inserting in a binary tree works. Finally, we will see some pseudocode for both operations. So what's a binary tree? Simply put, a binary tree is a graph structure where each node has at most 2 children. Binary search trees are another solution to the data dictionary problem. They implement search, insert, and delete. In addition, it can implement efficient range queries, where you can search from a particular key to another. If the tree is balanced, it has a worst runtime of order log n. Let's now have a look at some of its structure and terminology. A binary tree is a tree in which each node can have 1 child, at most 2, or even no children at all. The topmost node is called the root node, and is the only one without a parent. Nodes that have no children are called leaf nodes. Nodes that share a parent are called siblings. An uncle of a node is the parent's sibling. In a binary search tree, the left child of any node has a key less than its parent. Here, for example, we have a node with a key 4, which is less than the parent node with a key 7. This applies to every node of the tree. On the other hand, the right child of any node has a key that's greater than its parent. Of course, this applies to every other node in the tree. Let's now have a look at how to perform a lookup in a binary search tree. Say we want to look up a key of 5. Any operation on the tree starts from the root. If the key to search is 4 less than the current node, we move to the left child. In this case, 5 is less than 7, so we move to the left child node. If the key to search is greater than the current node, we move to the right child. In this example, 5 is greater than 4, so we move to the right. We stop searching once we find the key we are searching for. If there are no left or right pointers to take, it simply means that the key does not exist. The insert is very similar to the search operation. Say we want to insert key 3. Just like this search operation, we start from the root and choose left, since 3 is less than 7. At node with key 4, we choose left again, since 3 is smaller than 4. At node with key 2, we choose right, as 3 is greater. However, there is no right pointer, so we create a new node with a key of 3 and connect it as a right child of the current node. How do we model the structure of a node? At each node, we need to store the key. The type of the key used needs to be an ordered type. This is needed as searching in a tree requires comparing the search key with the node key. We also need to store the value associated with the key. At each node, we have a left child pointer and a right. The child pointers can point to another node, or in the case that the child doesn't exist, it can be pointing to a null. Let's now have a look at some pseudocode. For searching, we have a function called search, accepting a binary tree node and a search key. Searching for a key in the binary tree would start by passing in the root node. In the function, we have to take care of 4 conditions. The node might be null, for example when the tree is empty. The search key can be equal to the node key. The search key can be greater than that of the node key. And the remaining option is when the search key is smaller than that of the node key. When the node is null, it means that we cannot find the key in the tree. In this case, we can just return null. When the key is equal to the one on the node, it means that we have found our key. In such cases, we just return the value of the node. If the key is larger than the one on the node, we choose the right child and search recursively for the key. Otherwise, if the key is smaller, we choose the left child and again search recursively for that key. For inserting in a binary tree, we have to handle the same cases as when searching. The node might be null, the key is equal, the key is greater, or the key is smaller. When the key is null, we return a new node containing the required key and value. When the key is equal, it means that the node already exists. In such cases, we just need to update the value of the node. When the key is greater than the key on the node, we assign the right child pointer to the return value from the recursive call of the right node of itself. If the right pointer is null, the recursive call will create and return a new value. When the key is greater than the key on the node, we do the same. However, this time we use the left child pointer. At the end of our function, we return the node that we are currently handling. Binary trees are all about organizing your keys in an ordered structure so they can be accessed efficiently. In this video, we gave an introduction to binary search trees and discussed their structure. We have then walked through the insert and search operations. Finally, we have presented the pseudocode for both operations.